start this talk with introducing enamel. It is the most mineralized tissue in mammals. The minerals are formed by a process called biomineralisation. Unfortunately, the precise timing and spatial progression of biomineralisation is still largely unknown. And this information is crucial to optimize emerging biomimetic and regenerative dentistry routes. Therefore, my aim is to understand the temporal progression of human enamel biomineralisation. To do this, I acquired 4 archaeological, unerupted, developing incisors. The reason for that is it's highly challenging to get contemporary developing human enamel. And then I compared these teeth to a control, fully erupted, more than 8.5 years old. And the first technique I applied was X-ray microtomography, which is just a mini version of a CT scan. In here, the sample rotates, and at each sequential rotation, it's bombarded with X-rays. And this X-ray, the attenuated X-ray is detected by a detector, and then the cinograms produced are reconstructed into a 3D model, and from that 3D model we can get slices like this. Now each pixel of this image here has a specific linear attenuation coefficient. From this value, we can deduce the average mineral density, or whatever average mineral density this pixel has. The next technique I use is Synchrotron X-ray diffraction. For this technique, I use it to get texture, direction, and magnitude of crystallites. Before I move on, I would like to explain to you what I mean by texture. Texture, every single material have building blocks. When these building blocks have a, let's say, a preferred orientation, we call this material to be textured. Now, the magnitude of texture is a measurement of how aligned these building blocks are or how divergent. This technique involves hitting our sample with X-rays. The crystals within our samples diffract the X-rays, and then it's detected by the detector giving the following diffraction pattern. These diffraction patterns can be analyzed as a whole to get a full diffraction pattern, or we can choose a specific reflection to analyze, which I did in this research. So here's an example diffraction pattern of enamel. As you can see here, each circle of this diffraction pattern represents a reflection. I'm interested in this reflection right here, which is not a full circle, because we can get the texture, direction, and magnitude from that. How? Well, this reflection is related to the plane perpendicular to the long axis of the hydroxide crystal. How, you might ask? Well, let's see. This is our reflection. It appears like this in a 002 reflection curve. If we have a single crystal, it will appear as 2 dots at either side. So here we go, we have the direction of our crystallites. If we have a second crystal, it will appear as 4 dots, 2 dots at each end. Now if we have a powder sample, like for example a tooth, an enamel, we will have something like this. Now you can see the arc starting to form. This is a well-aligned probe region. Now, if it's less aligned, as you can see here, we will have thicker arcs because it's divergent. The crystal is divergent. I explained when I explained what texture was. Now, if you see here, when it's less aligned, the peaks are wider. When it's more aligned, the peaks are narrower. Remember this point. So we can get from this kind of curve, we can get 2 kinds of information. The first one is we can measure the full width half maximum to get the texture magnitude, and the second type of data is the texture direction from the peak's position. This concludes my materials and method, and now we can jump to results. From X-ray microtomography, I achieved the following mineral density maps. Least developed to lowest developed, blue being the highest mineral density, red being the lowest mineral density. As you can see here, this confirms that mineralization starts at the cusp and near the EDJ, and then progressing downward and toward the surface as a function of time. Also, the fully developed tooth is the most homogeneous out of the rest. The synchrotron X-ray diffraction results, more specifically texture direction. So I acquired, for each tooth, I've acquired an average of 5,000 diffraction patterns. And I drew the direction of each of the crystallites within these diffraction patterns. And I found that it was found that the crystallized direction is always approximately perpendicular to the EDJ, regardless of the development stages. This means that the preferred growth direction, the initial preferred growth direction persists from early through to full maturation. And the reason for that is, as you can see here, as early crystallites are laid down by amyloblasts, they don't change in direction, but they change in length, depth, width, and they don't change in direction. And that's why we have an increased mineral density, but no change in direction. Now, what I'm having in my results, I'm getting a graphs that look like this. It doesn't have a simple 2 peaks. I have 4 peaks here. So if you remember from my explanation, we can confidently say that the first 2 peaks are the ends of one population, while the second and the 4th peak can be the ends of the second population. I went on and I mapped the angular difference, and it was found that the angular difference is higher near the EDJ in all of my samples. Now, to make more sense of what we are seeing, I did some Scm analysis, and here you can see the 002 reflection curves that I talked about. Now, I want to concentrate on D for the moment, and you can see here, D has the 4 pronounced peaks. And look at how it's different than the rest of look at the Scm image, how it's different from the rest. Now, these lines here are the prism boundaries. In here, you see some prisms that are facing you, the lovely audience, and another reflection, the other prisms are facing other direction, perpendicular to that first direction. As you can see, we have this, and we have this, and that's kind of confirms that what we're seeing is 2 different populations of prisms. So the first 3 images here are A, B, C, which are the cusp. Third, the bottom images are D, E, F, less developed. And concentrate on F, B, and A now. Look at F. F has prism boundaries and also has dark areas between the crystals themselves within the prism. And then when we go to B, which is more mineralized, more developed, the spaces between the crystallites, I'm not sure if the back can see this, but we don't have these spaces between crystallites. We only have the spaces between the prisms, the prism boundaries. While at A, which is the fully developed, is here, we don't even have the prism boundaries. So we can assume that the spaces between the crystallites mineralizes first, followed by the prism boundaries, and so on. As you remember, from the 5,000 diffraction patterns, I extracted the full width half maximum of the peaks to see how narrow or how wide the peaks are, to get a measurement of texture alignment. And I did this for both of the populations. I didn't find any relation as we go in terms of maturation, but I found difference between the 2 populations. That always one of them has higher texture than the other, blue being the highest texture, red being the lowest. This indicates that the crystallites within one prism population are similar, while neighboring prism populations have different textures. I found no correlation between the texture, how organized the crystals are, and between mineral density. how much mineral there is. And to conclude, I would like to, we found that mineralization started at the cusp near the EDJ. Crystallized orientation persists from early through to full maturation. Neighboring prism populations, I have said, have varying crystallized organization, while crystallized with a single prism have similar organization. And the spaces between crystallized within prism mineralizes first, followed by prism boundaries mineralization. I'd like to thank these people for supporting me and for you kind audience for listening to me. Thank you.
Thank you, Mohammed. Please, some questions. Simon. No questions? Not one single intuitive question? Really, but it's quiet. It's work. I'm curious with the bimodal distributions of these. And you looked at human anatomy here, which has a certain pattern type, prism. I think just as an alternative view, but where indeed you probably got far more pronounced than prisms are just, you talk about first point, what the prism boundary is. What is a prism boundary?
Well, prism boundaries is that we have the interprismatic enamel, and in a way you have a keyhole structure, which let's say define this boundary.
If you talk to the first point, the prism boundary is actually a change in direction of crystals. So in a sense, you actually have that. You can actually measure that change in direction because you've got that from there. I'm just wondering whether you could also look at different types of enamel. You could have different prism types, or bovine enamel, ovine enamel, actually quite distinct prism pattern types, which is very different to human, and just to see whether you get those kind of distributions.
Yeah.
I don't want to say you can expand.
Exactly, but
I
Alan
need to look at.
yeah, I understand. But Alan claims in one of his papers that he can actually get all patterns that he talked about in one human sample. You don't need to go to other species. So maybe we're lucky enough to find all patterns within one human sample. But yeah, it's a good in a way to progress this research.
Maybe you've got actually there more defined prism boundaries.
Yeah.
A greater change of angle in the crystallized
Within the prism. Yeah. But as you can see here, this is 30 micron. So what we probe in an S-XRD is we're not probing interprism. We're probing
shapes here.
Yeah.
Any other questions for this? Fascinating talk again. We see the pattern here, across all talks, the biomineralisation. This is actually quite complex biomineralisation. No more questions? Okay. I managed to persuade you.
Have you looked at any 4s or 6s or any posterior teeth? Because that'd be quite interesting.
I only looked at central incisors and lateral incisors. I haven't looked at posterior as in molars.
Yeah.
There is studies that done by molars by the same group, but they haven't looked at the two populations. They kind of assumed it's one population as divergent in a way. Yeah, but it will be a very good next step.
It'd be interesting because the nodes and everything else, what's happened in nature, I think that's related to those plates.
It would be. Yeah, definitely.
Can you also look at aprismatic?
What happened is, so far, yeah, we can look at the future, but the spot size of the X-ray beam we use is 20 microns so far with these experiments. And the aprismatic enamel is less than that. You need smaller beam size to kind of study it.